Yeah, this is projecting some other. Okay, so this part will be about statistics and the use of non-standard analysis. So I don't know who knows anything about statistics. So also, I think if you want to be heard, then thank you. Yes. Okay. So I will have to try to not propose any statistics. That would be great because I don't get all that much statistics. And we try to I think it's on. Just
no, now it's on.
Muted. Yeah.
Okay. All right. So I don't know. Do we check or do we just? Should we just?
I assume that
someone will complain if it doesn't work. Okay. So a very baby introduction. So which one of these am I not supposed to write on? Here I can write on everything, right? Just the very back. Yes. Okay. So a very baby introduction to statistics. I mean, the situation in statistics is always that you measure a couple of quantities. You take something like n measurements, but they don't all come out the same. And then you have to find a way to deal with that, right? And someone, your boss or someone else, insists on you reporting just 1 or 2 numbers or 3 or something. And so you have to find a way of I mean, let's imagine that you're measuring, for example, the position of a star, and then you're convinced that the star has an actual position. And somehow from your measurements that unfortunately all come out different, you have to get to a star position. So what people usually do is that they take the mean, right? Yeah. And if someone asks you to find a measurement of how good your telescope was that you used to measure the star position, then what you usually would report is the following quantity, which people very often call sigma square hat, and that's the sum over the square differences, and then for some reason you divide by n-1, right? That's like a standard estimate of the variance. So if you've got a telescope, this could be a good quantity to measure the precision of your telescope or something like that. Did you already have a question? Okay. So, and the question I always like to ask at the beginning of this talk, Stevo has already heard it. I mean, why don't you divide by something else here? Or, of course, here you could also, instead of using the mean, you could also use the min of the xi plus the max of the xi divided by 2. And why don't you use that? And that's the kind of thing that statisticians think about. I mean, find a way of saying in which situations one of these will be better than another one, and things like that. And to focus your thoughts about this just a little bit more, or to tease you, I will now describe a little problem that I like. It's called, well, the problem doesn't really, oh, well, the problem has a name. It's called multivariate estimation of the common mean, estimation of the common mean in the multivariate normal location problem with 2 sample groups. So that sounds much more complicated than it is. So typically, I mean, you won't be able to say anything unless you make some assumptions, of course. And the first thing that you assume is typically that the xi's are identically and independently distributed according to some distribution. And the typical thing is that you don't know which distribution, because if you knew the distribution, then in a statistical problem, everything is settled. I mean, The thing is that you don't know the distribution. And very often you will think of this as being a particular distribution in a family indexed by some parameter. So this is called theta. This is called the parameter space. And you don't know which one. But of course, this could, I mean, for one thing, this could be all the distributions on wherever your samples come from, right? So where do your samples actually come from? So one thing that makes this a little more general is you just look at the whole vector of these samples and you let that be distributed, right? And then this vector is assumed to be in some element that's called the sample space, right? This thing here is called the parameter space. And then the assumption is this, that x is distributed according to some probability distribution. This is called the model. And this is a family of probability distributions on X.
Ask a naive question here.
Yes, always.
Since you're thinking of real world measurements, perhaps, wouldn't it make sense to, if the minimum or the maximum are way out compared to the others, to throw those values out?
That's what people do in practice. Yes, they get rid of the outliers. I've never saw a statistical, like a theoretical text that even mentions this idea. I mean, well, I mean, probably in practice you do that, but in theoretical statistics, this is not really something you think about. I think actually, I think this would be considered, after all that I know about statistics, I would consider this very bad. I wouldn't do that. But then, of course, I'm not like a practical person at all. Yeah, I think that's a way, that's in most circumstances, I would say that's a way of trying to make your model look better than it is. But don't quote me on this. Unfortunately, this is being broadcast to the whole world. Okay, I said it. And so, yes. Okay, so in any case, so I mean, is everyone okay with this notation? Because maybe you haven't thought about this since your graduate student days. So this just means that p theta is a measure, a probability measure on X, and X is in some set if and only if, and the probability that X, and we interpret p theta of B as the probability that X is in B, okay? So this is what this means. So these are measures. Okay, and the sample space is, of course, a measure space. And in a moment, we're also going to put a measure on this because we're Bayesians. So right here already, there's a big,
that they're independent with respect to each other. I mean, the definition of independence depends on the probability.
Oh yeah, exactly. So if you want to make this assumption here, which I actually, let's not. Let's just say this is just some, let's just look at the vector, and the vector is, let's just say this is some element of a sample space. Now this is a product space, and the measure happens to be a product measure. That's what IID means. Okay, but we don't need that at this point, or actually at any point in this talk. This is just a way of motivating that we're looking at this space at all, and it's also the case in most of the examples, or many of the examples. And it also comes up in an interesting way. In a second, I will come back to that. So that's actually a good point. So right here, there's frequentists and Bayesians. You might have heard of that. They have a conference every year that's called BFF, Bayesian Frequentist and Fiducial Joint Meeting. I think it's called BFF because Bayesians and frequentists usually are considered adversarial camps in the statistics world. But in any case, so here you can already say something about this, because the point is, if this is just a set, of measures and you don't know which measure you're looking at. That's what people consider the frequentist approach. The Bayesian approach would be to say that there's a measure on this space of measures, and you're picking a random measure, and your problem is really not one with a theta here. It's really a problem like this, but then you happen to be conditioning on some other random variable that you call theta. And that's the Bayesian approach to statistics. So already here at this sort of very basal level, there's a bit of a distinction. Okay, I said there's an example that I want you to think about, and it's this example. Oh, I'll put it here. So suppose that the vector space we're looking at, the sample space we're looking at, is what? I guess it's R to the 2n. So we'll have two sample groups, each of size n, and we'll assume that they're all IID. Each individual sample follows a Gaussian. Okay. So the probability of X being in B is proportional to just the Gaussian. So that's product of E to the minus, here is the mean. So they all have a common mean, which I call mu. Oopsie, what am I doing here? Okay, so that means that you have some sample groups, that you have samples, and each sample is distributed according to a Gaussian. We assume that they all have the same mean, and then we make a second assumption. We assume that the first n many of these variances are the same, and the second n many are also the same. So you've got two sample groups. In each sample group, they have the same variance, but you don't know the variance. All right. So I'll draw a picture. What happens when you sample from this distribution? You've got some mu, and then you take n samples from each group. You've got two n samples in total and n from each group. So the first n samples are the x's. They will look something like this, maybe. And then the second sample group is also n, and they will be the circles, and they look something like this. Right? So basically, you're measuring a star position, and you're using two telescopes, and you're measuring which is each of the telescopes. And then in the end, you want to know where your star is. Now, if you knew the precision of each of the telescopes, there's an obvious way to do that, right? Because so each of these sample groups will give you a mean. I'll put a bar on top of the mean. So you have a circle mean, and you have an x mean. But these two are not they're usually not the same, right? You don't get the same number. So what are you going to report as your overall mean? A standard approach that you could take would be, you could say, well, if I knew the precision of each of these measurements, I should take that measurement more serious where the precision is greater, right? If I've got a very precise telescope and a very imprecise one, then I should, weight these two means so that the more precise telescope gets a lot more weight, and the other one gets less weight. You could just take a convex combination of the two. So So call the two sample groups, the two samples x1 to xn and y1 to yn. So these are IID, and these are IID, and these have the same variance, and these have the same variance, but between the groups, they only share the mean, and they don't share the same variance, not necessarily, at least. Okay.
You said they didn't even share the same mean.
No, they share the same mean. They share the same mean. They share. Oh, the model, the distribution shares the same mean. The samples won't get the same mean. I mean, they will with probability 0, of course. Okay. All right. So then here's one way of estimating this, and it's called the Gray-Bill-Deal estimator. So it takes as input, of course, this whole sample vector xy, and you estimate the mean. How? Well, you look at. Oh, now I wrote S for it. Damn. Okay. Let me just change notation here, because I think throughout the rest of my notes, I'm calling this S. And I'll restore the n-1 here. So let's call this S. I'll just reuse this notation. So we take S1 squared over S1 squared plus S2 squared times the mean of X plus S2 squared over S1 squared plus X2 squared times the mean of the Y's. Oh, and of course I did this wrong. So this should be 2 and this should be 1. So what is this? So this is just a convex combination of the two, right? These two things here sum to 1. So we're letting the variances, the precisions of each measurement tell us how we should move between X bar and Y bar. And if the first measurement is more precise, this is large, so X gets more weight. And if the second one is more precise, this variance is bigger and Y gets more weight. Right? Does that make sense? So if you said, if one of these measurements would have perfect precision, for example, maybe X, the X group has perfect precision, then this is 0. And then you just report the mean in the X group, which is what you should do. Okay. So the point here is, though, that if we knew what these variances are, then there's ways to calculate that this is really a very, very good estimate. But we don't know what the variances are. So we're putting in an estimation of the variances here, right? This is also an estimate. This is also computed from the samples, right? So that's what's called a plug-in estimate. And no one has any idea if this is a good procedure in this problem or not. Very little is known about it. So that's why I mentioned it, because it looks very simple. But I'll tell you in a moment. I'll tell you some ways of making precise what you want for a procedure like this. So this is called an estimator. Okay, what you want from an estimator in order for it to be optimal, or at least not completely terrible. Almost nothing is known about this estimator in those technical terms. All right.
I mean, your example of the star and so forth.
Yes.
Rather where you don't essentially point rather than some more blobby type of thing. This is bound to give you a bad answer, because
Why?
well, you wind up with something in between the 2 points that this one says the star is here, and this one says the star is here, and so you're going to wind up saying, oh, the star is here when there's nothing there at all.
Oh, but this is exactly what would happen. I mean, so imagine someone tells you to measure where the star is. You have a telescope. You don't know the telescope, if it's any good or any bad. So you take some measurements. Then your telescope breaks after n measurements, and luckily there's another one, but it's a different brand. So you measure with that other one another n. Okay. then you have exactly this situation. The two means won't agree. Even though it's the same star.
Right.
So what are you going to do? You don't know what, I mean, of course you could, you could find ways of estimating the precision of your telescope, of course, but no matter what you do, the precision of the telescope is also an estimated quantity. So in the end, you will end up with something like this. So, I mean, actually, very likely this is how people do measure star positions, because I don't think they only use data from one telescope. So this is what happened. I mean, yes.
That's all right. I guess the web theory for that type of the empirical standard deviation does estimate the absolute standard deviation very well. The problem is here when we're mixing two different standard deviations.
Yeah, exactly. So the problem is that even though all you're doing is you're plugging this into a different estimate and a different estimator, all the known methods that you should tell you how this behaves, they don't work anymore. Okay, so yeah, that's a good point. You do know, so there is a very good theory that tells you that this is a good estimator, but that it sort of disappears as soon as you do very simple things with it.
But would it make more sense to say, of your two telescopes, decide which is the better telescope and take that as your finding a point in between that there's nothing?
Yeah, I guess, but then we were mathematicians. We don't do those kinds of things. We figure out, we take a piece of chalk and talk about things for a long time. I suppose you could just build a better telescope or something like that, but then you wouldn't be doing statistics.
But that would just be a different estimate. That would just be selecting either an X or Y.
Oh, that's okay. Yes. Oh, that's a good point. Yeah. Oh, if that's what you're saying, then I didn't understand the question well. I have no idea. Yeah, I don't know. That's a good question. You're just saying throw out one of the estimators, the one which looks like it's, but that's just, okay, so that's just saying, take the minimum, yeah, exactly. You look which of these two is higher and you just soup it up to one or something like that. Yeah. I'm pretty sure that that you can show that this one does better than that. I don't know. It's a good, so we'll have to, so good, because now we'll have to get into what does it mean for an estimator to do better than another estimator. We don't even have a language for that. And so one way of doing these things is called statistical decision theory. And there are others, I suppose, but I haven't gotten there yet. So this is where we started. It's also a very, very influential theory. I mean, somehow everything is inspired by this, at least to a degree, I guess. So what is a decision problem? There's an abstract notion of decision problem. So, I mean, you might know that one of the reasons that people like the mean is that it minimizes some sort of square differences, right? And so basically this is one way of gauging the quality of estimators. So formally, a decision problem, let's just make a definition. A decision problem is it's just a tuple. It's got lots of components. It's got the sample space, which we already know. It's got the parameter space. It's got the model. And then it has something that's called an action space and a loss function. And a class D of relevant estimators that we're considering. Okay, now I'll have to say what all of these are, such that, so theta, I've already said this is the parameter space. I'll write it again. Is a measurable space. We still haven't seen why it's a measurable space, but we will soon put a prior on it. So there you go. So X, that's the sample space. It's also a measurable space. Okay, then we've got A. So what is A? A is called the action space. Okay, and what is the action space? Well, it's where the statistician chooses their estimate. Okay, so the The statistician takes an element of the sample space, and they're supposed to do something, report a number, an estimator. But the reason why people introduce this A is because maybe they also just want to report whether some hypothesis is accepted or not. So they might just respond by saying 0 or 1. And to cover all of these things, people introduce the action space. So it's just the statistician observes a sample and is supposed to take an action in the action space. And this is also a measurable space. Okay, so what is L? L is the loss function. So L takes an element of the parameter space and an element of the action space, and it produces a real number. And let's assume that the real number is positive. Actually, for most of this talk, I don't have to do that, but it's somehow traditional. So I will do it too. So what is a good loss function? I mean, this could be any function at all, but a very common loss function is square difference, right? So so let's put an example. If theta is R and A is also R, or maybe Rn, then something that people frequently do is just the square of the Euclidean distance of the two. So, I mean, what is
Lambda is in the action space and theta is in the parameters.
Yeah, I'm just assuming that they're the same. So I'm really sorry. This is kind of notationally involved in all of this. It's very general abstract nonsense but the point is that, I mean, so consider that you're in a very simple estimation problem where the parameter space is just the mean of your distribution that you want to estimate, and the action space is also just wherever this mean could lie, and your task is to figure out what this mean is, right? Then your loss function would just say, well, you're this far off the true value. But of course, it could be the case like in this model here that we looked at. Yeah, okay, maybe write this down as an example. Why not? So in this problem here, what are the different things? So theta is the set of the common mean, the variance of the first group, and the variance of the second group, right? Oh, better be greater than 0. So this is the sample space, right? And what you want to be, this is the parameter space. I'm very sorry. And I guess the sample space is just R. And then the action space, I already wrote down what P is, right? That's now the parameter theta is just the mean and the variances. So that's a family of, your measure is one of a family that's indexed by finitely many real parameters. Actually, just 3, because we're assuming all these variances to be equal in each group. Okay, and what is the action space? Well, the action space is now just R again, because you're just estimating this guy. And you forget about the other two. They're called nuisance parameters. You ignore them. So typically what you will be estimating, so the statistician typically estimates a function of the parameter, right? In this case, it's just a projection to the first coordinate because you want to get rid of the nuisance parameters. Okay, but I'm sorry that this is a bit abstract, but I didn't make up this theory. Okay, so what have I got? Everything? Oh, and I forgot D. So what is D?
D is just the parameterized measure. Okay?
Huh?
The third coordinate P is the parameterized.
Oh yes, I forgot that too. Yes. Okay, let's put that here. 5. P is a family like this in the non-Bayesian approach, but that's sort of in this general definition of decision theory, you're not supposing yet that there is any measure on theta. So, okay, so it's just a family of probability measures on the sample space. That's all it is. And your goal is, so in an estimation problem, your goal could be you want G to be equal to, you want A to be equal to G of theta, right? So that's maybe a little more general. Maybe you want a G here. So that would be a very typical loss function in an estimation problem. You're estimating G of theta. So your action is supposed to be a value of G of theta, and your loss function just gives you how far you were off the real G of theta. And a different loss function in an estimation problem would be maybe this, just the absolute value. Okay. Okay, and now, yeah, five. And now finally, what is D? So where does what does the statistician actually choose? So the statistician is supposed to choose an element of E. And such a thing is usually called delta. What is delta? Delta is a function from X, because a statistician observes a sample and he takes an action, right? That's what he does. So in other words, D is a set of functions from X to A, and then you say they're regular enough so that everything that I say later will make sense. I mean, sooner or later, I'm going to be writing down some integrals, and you want these functions to all be nice. Okay. So, okay, so how does that help us at all? Well, now that we have the loss function, we can calculate the expected loss for the statistician if he follows this rule. If he always follows this rule, what loss does he expect? And of course, that's just an integral. So, okay, so the expected loss is also called the risk. So now you introduce the risk function, and this is always done the same given these ingredients. So the risk function depends on the true parameter. This is, I mean, these are also sometimes called the states of nature, right? The reality, the true probability distribution, which we don't know, and whatever choice the statistician makes for an estimator. So in our example on the other blackboard, this would be the actual mean and the Gray-Bill-Deal estimator, for example. And we can look at how does the Gray-Bill-Deal estimator perform in the sense of what is its expected loss if the actual state of affairs is a particular one, if the mean has a particular value. Okay, so what is this? So it's the expectation of the loss. That's really all it is, conditioned on theta. So why does this make any sense? This makes sense because this is a random variable, right? So I can insert it into this function, insert that into the loss function, and then I can just take the expectation value conditioned on theta because it's a random variable. And in case you're not completely happy with that, let me just write down the actual integral. So what is it? It is the integral over all L delta of x. Now, delta of x is an individual sample. And we have to integrate this over the probability distribution. That's what it is. That's all there is to it. Okay, fine. So that reduces some of the information, right? Before we had like, okay, there's some, the statistician takes an estimator. There's a lot of random variables floating around. Now to every estimator, we've associated one function. It's called the risk function. And we can compare risk functions.
The way you write it, P theta dx, I'm misunderstanding. P theta is the measure.
Yes.
Why don't you write D of P theta x? Why did you put it that way?
Oh, I'm sorry. This is something I've gotten used to with the statisticians. So this just really means the same thing. I'm integrating over that measure. I'm just marking the variable x as the integration variable. So this is just, so if you want, this is. Okay, right. But people use this a lot. I mean, so I guess one way of making this precise would be that you know this could be a density or something like that. But I don't know. We don't have to do that. That's fine. This should, yes. Yeah. Yes. Yeah. This is, it looks, this looks crazy. But no, but people write that a lot and it's very useful. But yeah, okay. This is the official definition. Okay, let's see. Right, so one thing I should talk about is randomization. Because this is actually not general enough for most purposes. Because in very many problems, the statistician will have absolutely no chance if they are only allowed to pick single actions. And that is why we allow them not to choose a single action, but we allow them to choose a probability measure on the action space. So they're allowed to take a randomized action. Okay. That sounds fancy, but it really doesn't change anything at all. Now, what do we have to do? Now we have to integrate again. Let's start here. So now this is a measure. D of x is a measure now. So we should be integrating over this measure. Okay. So in the randomized case, so this is the non-randomized case. In the randomized case, you have L theta some action, and now you're supposed to integrate over delta, where this is a measure on the action space, and then you're integrating over dp theta.
Wouldn't that just give you a new loss function, which was the integral of the old loss function over the M1A?
I guess so. Yeah, that's true. But the point is, you've then enforced convexity. Because now the deltas, if you've got this, I mean, these deltas you can form convex combinations of, right? I mean, that's really what it is. It's the convex hull in some sense. It would actually be fine to have finitely supported probability measures here for most of my purposes. But what this really is you're sort of taking some nice convex hull of the space you're interested in, and you're really just enforcing that the loss function is linear in this coordinate here by taking this measure. So you're right. So we could also just say, or we say the action space is convex, and we assume that we assume that the loss is linear in the action, and that's very helpful. Okay, so that's randomization. And here, this is also the reason why I like to use d of a and d of x, because then I don't, this looks very, I get lost in this expression. But if I write it like this, I don't get lost. Delta of dA p theta of dx. But it's supposed to mean the same thing. This is a measure. This is a measure. I'm just marking the integration variables. I mean,
It's all in first year calculus.
And now we're doing first year statistics. So this is why, yes, exactly. All right. So Now that we've got, now each delta in D has a risk function. And this is called R delta. And it goes from the parameter space into R. And now we can compare these. And that's still not too great because that's a space of functions. So you know that we still quite complex to compare to functions. Of course, you somehow want the functions to be low, right? Because big risk is bad, small risk is good. So one thing that would be great, one thing that is clear is that if something is everywhere less than the other thing, that's desirable, right? So people give a name to that. They say delta 1 dominates delta 0 if and only if for all theta, R theta delta 1. Oh no, let's not define dominates. Let's first define delta 1 is at least as good. At least as good. If the risk lies everywhere below, right? Now, that happens sometimes. For example, in the normal location problem, so if I just look at estimating the mean of a Gaussian from which I take n samples, then the risk function of this estimator is just constant, a constant function. And if you only look at unbiased estimators, that is ones that on average center around the actual population mean, then this risk function will be less or equal to every other such decision procedure. So there are cases where you can already pick, you can pick a best estimator. So that's what's called a best unbiased estimator. So maybe I should say that somewhere. Delta is unbiased for an estimator. Okay, this is really not. You know what? Let's not. I'm starting to tell you too much about statistics, and I won't ever get to our theorem if I keep going like that. So this is what it means to be at least as good. So that's a partial order, right, between decision procedures. And every partial order has a strict part. So let's write this also for this partial order. And then the strict part of this is called domination. Delta 1 dominates delta 0. And what does that mean? Well, it just means that one risk function is below the other one, but they're not equal, right? So let's write it down, though, in detail. One always does better in risk, and there is some point where the risk is strictly smaller. Okay, so if you've got a decision procedure that's dominated by another one, there are really not a lot of reasons not to switch to that other one. You should switch to that other one, and that's why people call delta admissible. Among some class of decision procedures, among some C in D, if and only if there does not exist a D1 in C such that D1 dominates delta 0. Okay.
I have a quick question about the risk functions. I have a quick question about the risk functions.
Yes, of course.
Which is, normally you have, I guess, a reward for your risk. So is this risk function, I guess, incorporating that?
Oh, that's a good question, actually. Yeah, so one reason that people came up with this stuff is because it was the late 40s and early 50s, and game theory was on vogue. In game theory, so you could think of this as a game. And the game would go like this. There's two opponents. One is called nature and the other person is called the statistician. Nature chooses an element of the parameter space and the statistician chooses an element of script D. And then they settle up using the risk function. And in this sense, so the statistician would pay nature some money or something like that. But the point is, and this is what makes statistics different from decision theory, is that nature doesn't really care. Nature is not, as they say in many statistics books, they're not plotting, nature is not plotting the demise of the statistician. Nature has no desire to win or to make your risk be large or something like that. So nature doesn't gain anything. No, I guess this is really your question. Your question was, I mean, is there a reward for the risk? No, there is no reward for the risk. In game theory, the reward is not losing, right? And the risk is playing at all. So in game theory, you should call this you shouldn't call this the loss. This would just be the, I don't know, this is the amount of money that the statistician has to pay nature or vice versa. Right, who wins and who loses is just a question of where you put the zero.
Okay, yeah, so I guess it sounds more like a reward function instead of a risk function, but that's, I guess, just semantics. So yeah, thank you.
Yes. Okay, so let's see. So in order to be able to tell you my theorem, I also have to introduce a second notion of optimality, and that's called Bayes optimality. Okay, I'm going to be way over time. That's very bad. Oh well. So, in the Bayesian approach, as I already said, we consider theta, little theta, to be a random variable. So that means you fix a probability measure on the parameter space, and this is called your prior probability. Okay. And then you have a very easy way of totally ordering these decision procedures, because now you can integrate over theta. So you can call, you define the Bayes risk of a procedure with respect to pi as the integral over the risks where your integration measure is pi. Now that's just a number, okay? And now you can compare procedures again, and you can say delta is Bayes among a class if and only if it has minimal Bayes risk. So our pi, well, Bayes among C under pi let's call it delta 0. If delta 0 is the min. Or let's call it like this, because who knows? Yeah. If delta 0 has smaller Bayes risk than everyone in D. Okay.
These measures are positive.
Yes, it's a probability measure. That's what.
And one is usually the definition of a sign.
Oh, so what is the definition of an unsigned measure? P. Oh, God. Like this? I can't get this right. Last time I gave this talk in front of you, you had the same complaint with a different notation. Yeah, absolutely. This is supposed to be a probability measure. I'm very sorry. I'm just using the notation wrong. Okay. All right. Okay, so these are two ways in which a decision procedure can be optimal or non-optimal. Now, the thing is about the Graybill deal that I showed you earlier. This is not known if it's admissible. It could be that it's dominated. Actually, I'm not sure. I think it's also known that it's not Bayes. It's also not known if it's even if you restrict the class of decision procedures to which you're comparing it, not a lot is known. So if natural classes are so-called equivariant decision procedures or unbiased decision procedures, and in those, it's also not known if it's admissible in these classes or anything like that. So it's typically very hard to show that something is admissible. And sometimes arguments use Bayesian methods to show that something is admissible. That's actually something that I will get into now.
Less to check.
Hmm?
Because there's a less to check.
Yes, exactly. Yeah, you just find a pi, and then you just calculate.
Check all the space.
Exactly. Yes, absolutely. And so, I mean, so in some sense, also that the game theory analog here is useful because sort of, this is kind of an unfair setup, right? Nature chooses a point from this space, and then the other player gets to choose a measure, right? So it's very asymmetrical. And actually, if you let them both choose measures, it's a lot more. It's a lot more symmetrical. So that's also one reason why. Another reason why someone might like to look at priors is because as I said earlier, it's somehow unnatural to say that there is some set of probability measures here that you're talking about. Why don't you just start with a single one at the beginning, and then actually you could go up here again, and you could say, well, you don't talk about IID ones, you talk about something that's called exchangeable ones. And you put this away. Whenever you have some finitely or even infinitely many random variables which are exchangeable according to some probability distribution, exchangeable means that the distribution doesn't depend on permuting the random variables. So the index of the random variable doesn't carry any information, which is a very mild assumption. Then actually you can show that X is IID on P conditioned on some random variable theta. And this random variable theta, that's called de Finetti's representation theorem. And then this random variable theta you can interpret as a prior on a parameter space. It's a very nice, so that's a very nice aspect of the Bayesian theory. Okay, in any case, I'm getting carried away a little bit. I want to.
What about the existence of these things? Why is there?
Oh yeah, those are all very hard questions. There might not be.
There might not.
There might not be. Yes. For example, like the usual mean. This thing here. Okay, so here's some fun things that I always like to tell people. So suppose that all of these are again normally distributed. In Rn. So each x is a little cloud, right? And they're identically normally distributed Gaussian, right? Okay, it's a very easy problem. If n equals 1, then this estimate here is admissible. And you can show it is, but it's not Bayes. It's generalized Bayes though, which means here that you allow that you forget about the normalization. You allow measures. If you allow measures here, then it's Bayes in that sense. So it's generalized Bayes, and the measure is of course the Lebesgue measure. Okay. If d equals 2, that trick doesn't work anymore. It's still admissible, not d. If n, this should be d. We've got an n. So this is d. The number of samples is n, but we're talking about the dimension now. If in dimension 2, this estimate is still admissible, but it's not Bayes, and the proof that it's admissible is pretty hard. It's also not known to be generalized Bayes. If d is 3 or higher, this is not admissible anymore. You get an estimator that performs uniformly better if you shrink towards a random point. And by random, I don't mean random I mean, you pick a fixed point at the outset, the 0 point, you shrink towards it. You get an estimator that has uniformly better risk. That's what's called the bias variance trade-off. That shrinkage estimator will have bias. It will always go off into a particular direction from the true value, but perhaps by a tiny amount, but it will still perform better in terms of the risk, in terms of the expected risk, and quite a bit better actually. If you like this, as I said, the X bar has constant risk, and the shrinkage estimator looks like something like this. And that was not known until the 60s. And everyone went a little crazy when people learned about that. It's called Stein's paradox. And it's used in machine learning today because you want to sometimes reduce. I mean, so, you know, somehow the idea of, oh, well, I want to tell you my theorem. I just keep talking and talking about statistics, and I will never tell you my theorem if I continue like that. Okay, now I'm going to use that blackboard. Okay, can you see the whole thing? Yes. Oh, okay. Can I even already tell you my theorem? I probably can't, because I need to remind you of some non-standard analysis basics before I do that. Okay, so I have to introduce more notation, I guess. So a quick primer on non-standard analysis. What do you do there? What you look at is an elementary embedding. So you fix an elementary embedding. It goes from a universe of this form, where I mean these to be OR elements. They don't have to be actually, but that's how people usually do it. So you fix some sets that you want to be fixed under the elementary, and you fix some sets whose points you want to be fixed under the elementary embedding. That's just the traditional way of phrasing it. It's not, there's nothing deep behind it. And then you've got an elementary embedding from this set here to somewhere. This somewhere is usually called star V of the same stuff. And what do you want? You want, first of all, that star is sigma 0 elementary. In a language where you've got constants for everything. Okay. You want a star of x equals x for all the elements in this, for all OR elements. But this is just beautification.
Doesn't this follow?
If yes, I mean, yes, I guess it does. I'm sorry. Yeah, I mean, if it, yes, okay. I don't know if it follows. It depends on how you define all these things. Pardon? I have. Where here? It's a language of set theory. Okay. All right. I don't want to. With constants. Yeah. I mean, you know, it's very hard to know when to stop being precise, but apparently I should not stop so soon. All right, so what is the third one? Well, the third one, if for us, will be saturation. Star is saturated over Vx. Okay, so what does that mean? That means it means for all n if you've got a filter on some level, so this has a finite intersection property. For all such n, you can shove over the elements via the elementary embedding. And on the target side, you will get something in the intersection.
All, in particular, all the clusters get serialized.
Yes,
All the clusters are such a huge index.
yes. Yeah. This is actually not a very, I mean, this is, you can get this much saturation just instead of C. This is not like there's stronger saturatedness axioms, but okay, so we fix this and then we can prove a theorem. Let's see. So what does the theorem say? Okay. Given any decision problem whatsoever, and a convex set of decision procedures, delta zero is admissible among C if and only if there is what we call a hyperprior. So it's just an element of the star of the set of priors. I'm very sorry, stable.
Maybe I'm curious how this D is related to your space there.
Yes,
Script D, what as an object.
script D is just, we fixed it at the beginning in the decision problem, right? So it's a set of functions from X to A, right? So something of the order from functions from theta to theta, you know.
It is a subset.
This is a subset of functions from X to A.
And in your space, you said, it's a subset of your space, the omega R that you mean.
Oh, I see. That's why I made the dots here. So theta, A, all of these things should be OR elements.
Oh.
Okay, yeah, okay, that wasn't very clear. So I want all the parts of the decision problem to be OR elements. Or if you want in the space is enough. They don't have to be OR elements. You assume that the decision problem, so given a decision problem in here, okay? That's what I should have said maybe. But somehow, I mean, you just assume that this is the whole world. I mean, okay. Then you're admissible if and only if there is a pi such that your Bayes among the standard decision procedures, not among all the star of D, but among, or the star of C, but among the pointwise image. Okay, so there, I'll write this down. There is a pi such that for all delta in C, if you want to take the risk with respect to pi, you have to star the risk, of course. And since we're talking about a standard delta zero here, we have to star the standard delta zero. So this is less than or equal to pi star delta. That's it.
So pi decides all the standard.
Yes,
Relation between the standard.
it's only decides all the standard ones. Yes. So that's it. And then, I mean, actually, there's a couple of other theorems that I would have loved to talk about.
The delta zero, what do you mean it's besides already? So for every standard, for everything you see.
So first of all, this is a decision procedure, right?
Oh, I see. So, and that's in the ground, like, what is that characterization of,
The characterization of what it means to be admissible. So oh, and I'm not done yet. Sorry, I'm not done with writing down the theorem. Oh, gosh. And pi has to do one more thing. And for all standard points, they all get charged. Okay, very important. Otherwise, this is not equivalent. Okay. Right. So what does it mean? It means, well, I mean, we would all love to have lived in a universe where admissible is the same thing as being Bayes. Yes, there should be a star. No, I think this is right. Because theta is supposed, if you want, put a star here, but theta is an OR element for theta consists of OR elements for us. You want me? I can put a star. That doesn't make it wrong.
but pi is supposed to be a measure.
Yeah, it's actually going to be hyperfinitely supported. The pi that we construct in this theorem.
Has a lot of atoms.
Yes. Yes.
Atomic.
It's an atomic measure, and the support is star finite. Yes, but that doesn't have to be the case. I mean, this is not. It's not that, you know. I mean, we know of cases where you get non-atomic measures. It's not that non-atomic measures. You know, you could artificially make this non-atomic if you want. We have examples where you produce non-atomic measures by the same methods. The point is really that atomic ones will do, hyperfinitely supported ones will do. So yeah, actually, so star of V will think that the support of V is finite. So star finite, if you like. Okay. All right. So
Why is he saying that this delta zero is big?
yeah, it said it. Well, first of all, this isn't the prior. So there's a weird kind of asymmetry here. There's a weird mix going on. No, because this set here and this set here, they're not elements of the alter power or of the star world, right? They're what's called external sets. So this is a subset of some Vn, of some star Vn. Well, actually, this is a subset of star D, okay? But it's not going to be an element of the structure on the right.
So he is not one of the things, one of the constants in the original.
Oh, it is. But when you shoot it over, it becomes star of C. So the target model can talk about star of C, but star of C is much bigger than C itself. Okay. So actually, one thing that might be interesting to note here is that the saturation is equivalent to having hyperfinite covers, right? So for every x in V of R, there exists an x twiddle in star V of R, such that star V of R thinks x twiddle is star finite. And okay, and from the outside, you can see that x is a subset of x twiddle.
In the star, the pointwise image.
Yes, I do. Exactly, thank you. Yeah, that's called hyperfinite covering. That's equivalent to this saturation axiom. So if you wanted, you can say you could, you know, the support of pi will be a hyperfinite cover. And actually, you could also say that delta 0 is admissible among a d-twiddle, is star base among star base not okay. Maybe I should write this down. You could say that you could say here equivalently that delta 0 is admissible if and only if it is star base among twiddle C for a hyperfinite cover twiddle C of C. Okay, so these external sets here you could replace by hyperfinite covers. You would still get the same theorem. Yes.
Let's go back to the original introduction story.
Yes.
That was everything is fine.
Finite. Yes.
Is there a solution?
Yes. So that's actually
That's because that must be because here you are probably using the fact that things are finite.
exactly. So I mean the proof of this whole I can sketch the proof of this whole theorem, and it's actually not very hard once you have it. I wonder what I should erase. I'll erase these examples. And you can write on those? Okay. That's nice. Why somehow I was told I should never write on those. I forget why. Oh, I know. Yeah, I don't want to move it. Okay, that's fine. So this is where I put the proof. So sketch of the proof. So okay, so we've got so one direction is really easy actually. If you've got this strange mixed situation where we call this star base among the standard part copy of C with respect to a prior that charges every standard point. That's the relation. There you go. That's the relation to being base. It's not being star base, because if you were star base, you would have to put a star here. And if you wanted to charge every point, you would have to put a star on the theta. That's not what's happening. You charge every standard point. You're minimal among the standard part copy. So this pointwise image is sometimes called the standard part copy. So you're star base among the pointwise image under star with respect to a prior that charges every standard point. That's what it means.
But the charge for most standard points is going to be infinitesimal.
Yes, of course. Yes, this is why you do this, right? Because I mean that's a completely classical thing actually. If you have a prior that charges every point and you're base under it, you're also admissible. Unfortunately, that's not very useful except in countable spaces. I could prove that. Should I prove that? Maybe let's prove that. So this is the easy direction, very quickly. So fix delta 0 and pi, as in the second part of the theorem. Now suppose that delta 1 dominates delta. That means the risk function is everywhere less delta 0. The risk function is everywhere below, but also there is a theta where it's strictly below. Let's write it like that. Theta delta 1 is less than our theta delta 0. But our prior charges this point. Right, so the risk under pi of delta 1. Okay, now I have to do some algebra. How do we do it? Yeah, let's calculate what's called the excess base risk of delta 0. So that means you take the base risk and you subtract the base risk of the person that you're comparing it to. Okay, so what is this? So that's the integral over R delta 1 minus R delta 0 under d pi. Now, okay, so this here says this is always greater or equal to 0, right? And this here says there exists a theta such that pi at this theta is bigger than 0, and R delta 1 minus R delta, R delta 0 minus R delta 1 at theta is strictly bigger than 0, right? So the whole integral has to be strictly bigger than 0. And that's it. So delta 0 has positive excess base risk. That means it certainly wasn't minimal. It didn't have minimal excess. It didn't have minimal base risk. No. It works though. Okay. It works. There's an easy version of this for continuous risk functions, right? If risk functions are continuous and every open set gets a positive measure, then this also works. And this is in a lot of classical theorems. This is used in practice a lot to show that things are admissible, actually. So what you can do if you want, you can introduce, that's what we did in order to be able to prove a lot of these theorems in one go. We said we introduced a separating family. So you call a subset of the power set of theta a separating family. And now you just write down what you needed of the singletons and of the open sets in order for this proof to go through. And it's kind of silly, really, but it's nice. So what do you need? So it's a separating family for your set of decision procedures. Well, let's say for the total set of decision procedures, if and only if, whenever you've got two decision procedures, and their risk functions are not equal, then there is an epsilon, and there is an element of the family where on the whole set they're different by at least epsilon. So how do I write that? For all theta in B, R delta 0 at theta minus R delta 1 at theta is at least epsilon. Actually, I want this. Maybe I want to know which one is bigger. Okay, I guess that's what I want. So somehow, it's not really about being a atomic measure or being an absolutely continuous measure. None of that matters. What matters is that you can control what your measures do on a separating family. So you've got to have a separating family, and then you try to control what your measures do there.
Okay, well, the separating family, you are reducing this complexity of singleton to something roughly in the logarithm, of the, you are reducing your problem with the about the atomic to a coordinate, basically a coordinate. So you see what this separating family is what people do this every set of size continuum. There's a counter separating family.
Yes, yeah.
So the reason is because you cannot have a continuum many positive atoms.
Yeah.
On many measures.
I wish we'd had we didn't even have to use anything that sophisticated.
I'm just saying, the
I wish.
of that sort.
Yes.
You cannot have a continuum many positive atoms, but you can have positive numbers on
I mean, this is at this point, this is really just a convenient way of speaking and of making these theorems abstractly more general. But that does have an application if I had more, because so one thing that you want to do is, so this prior here, this prior that I constructed here, I didn't, but I could if I had more time. This comes from a saturation argument, of course. And if you want to convince statisticians to care about this prior, that's kind of hard. And also, it's not, it would be nice if we could say more about what this prior actually looks like. So there's ways of showing that things are admissible where you're given a family of priors with a certain property, and then you say something about these priors, you get out that you're admissible. So maybe you want the prior witnessing this to be a member of that particular family. And then you very quickly run into such arguments.
If they have such a problem accepting this,
Hmm?
if they have a problem accepting this as a reasonable prior, then they need more information on it. Then you can ask me a very analogous question. Why don't you give me information about your seed?
Yes, it's true. Yes.
That's
Yeah.
the problem. Why just people
Well, I mean, I should say exactly.
How can you ever cite arbitrary seed?
And I should say there are theorems about C's which are less arbitrary, right? I will read one to you. I won't write it on the board. So suppose, for example, suppose that A and theta are compact subsets of Euclidean spaces, and all decision procedures have continuous risk function, and the loss function is continuous in the action coordinate, and the model admits densities with respect to either the Lebesgue measure or the counting measure for every theta, such that the map, so that sort of the family of density is jointly continuous in some sense, then every admissible decision procedure has a Bayes decision procedure below it. So, instances of this are known. You just have to ask a long list of things about the problem. And I have here, can't write, there's no way writing these on the boards, but I have like 5 theorems here that are similar. They make different kinds of assumptions on all of these elements, and then they always tell you either that every admissible procedure has something Bayes that dominates it, or has something Bayes with a risk function less or equal to it, or it has something that's Bayes but with respect to a measure, or in every neighborhood of it there is something that's Bayes, things like that. And you read all these theorems and you start thinking, there has to be a better way. And hopefully this is it. Because so what we're trying to do now, of course, is we're trying to take this and prove all these theorems from it. And for some it works. For 2 so far. And probably soon for all of them.
This theorem gives you an abstract way of saying, how do I make better and better priors, right? This is this must be the kind of saturation argument, right?
Oh, yeah. I mean, there's one thing though that you have to be aware of. Being admissible it does not mean you should use this procedure in the real world, right? It doesn't tell you anything about the real world. So the Bayesness here isn't about the real world. It sort of says that if your procedure is admissible, then there is a possible world in which it describes the world very well, right? This is really something about, I mean, I don't think it doesn't. There are very silly procedures that are admissible. Constant procedures are admissible in most problems, because there is a sort of, if you're convinced that the real value of theta is something, right? That in a typical problem, that will be admissible, because no one can outdo you if if that should be the case. And there's also a prior which makes you Bayes. It's the Dirac measure at your fixed idea, right? So it doesn't. Yeah. So I'm saying, what I'm saying is that delta zero appears in this theorem doesn't tell you that delta zero is necessarily optimal. It just tells you that it's not, there's no obvious reason to use something else.
But what about asking questions about the optimal, the maximum? We can also ask, if there are missable deltas. The best one.
It's very hard. So it's time to draw the picture. I can, so this was just one direction. I should have showed you the other directions.
Another empty body.
Okay. Well, it's very, very nice. So let's assume that theta has only 2 points. Okay, it's a very simple world we're living in then. But that's really nice because now I can draw a complete decision theoretical problem on the blackboard. Okay, I just make the two axes, delta 1 and delta 2, theta 1 and theta 2, right? And now a risk function is a point in this space. So maybe this is the risk function of delta 0. This is its risk under true state of nature being theta 2, and this is its risk under the true state of nature being theta 1. And now you've got some of these procedures here. Now, that the set C that you're interested in is convex means what? It means that your risk set is a convex set in this space. That's because by randomization, the risk is linear in the argument delta. So C being convex just means, that and this is called the risk set. Okay, so the set R delta, where delta is in C, let's write R upper C for it. This is called the risk set of these decision procedures. Now, what does it mean to be admissible? Admissible means that you're on the lower boundary. So if you look into the lower quantant below you, there's nothing there. That's what it means to be admissible. And what does it mean to be Bayes? It means there is a prior such that you have optimal Bayes risk. A prior is like a hyperplane. I mean, it's a line in this sense. And if this is your line, for example, Bayes risk of a particular procedure is this normal distance. That's the Bayes risk. So this delta 0, for example, is Bayes under this prior, because if I move it up here, then it gets optimal Bayes risk. But I mean, this delta 0 is also Bayes, just under a different prior, namely this prior, right? So there's a lot. So the admissible ones are the lower boundary. In this case, that's just this line here. And the admissible ones are also exactly the Bayes ones. And that's actually how we prove this theorem. So maybe I get to the proof. So this is once we had it, it was very, very simple. Here's the theorem. If theta is finite, and D, or let's call it, no, it's called C here. And C is the convex hull of finitely many procedures. Oh, this doesn't have to include delta 0, actually. So let's write it like this. Then delta 0 is admissible among C if and only if there exists a prior well, it's Bayes with respect to a prior which charges every point. That's it. So delta 0 is Bayes among C under pi, and for all theta, for all little theta, pi of little theta. I won't write the singleton sign brackets now. Is greater than 0. So in a finite problem, this is true. Your Bayes if and only if you're admissible if and only if Bayes under a prior which charges every point.
Then you have this marginal fact about arbitrary convex set, and instead of these delta 1, delta n to the extrema points. Very like this.
Again?
Instead of having set C.
Yes.
To the extrema point, you're very likely using the That you are finitely many external points. right?
Absolutely, yes, yeah, that's important. So you're saying it put what
Yeah,
instead of
can
C?
can you state your theorem in more general form to talk about the external points?
Extremal points.
Because every convex set is spanned by external points.
Yes, I mean,
there
it's
are-
just saying
There,
a convex set with finitely many extremal points. That's exactly what you want. The different. Oh, you meant a compact set of extremal
for
points.
example, you have in a, what you will be the problem if you have a disk. because
Mhm.
all of them are external. So I mean, there's no difference.
In a disk, that's not convex. So you want your
I mean, that's
oh a filled out disk. Oh, yeah, it's not the
then everything
yes.
is there. So it's like only there are a huge number.
Right.
It's a similar case.
Yes. Yes.
So here, yeah,
You're right. Actually, probably, this is, I mean, to prove that theorem, this is all you needed. But you're right. This probably doesn't just work for finitely many extreme points. You could probably, Yeah. yes, yes, that's a good point. Yeah. And actually, well, we use the finiteness, but actually, one thing one could do is one could use that theorem and lift it, because if your set C is very nice, then you should be able to pull back the pi into the standard world. I mean, this is sort of the game that we intend to play. It doesn't really work in many cases yet, but that would be nice. But I guess from this, you can almost see how to prove that, right? I guess you can see how to prove that, because what you do is you take a hyperfinite cover of D and of theta, and then you apply the star of that theorem, and that's it. You're done.
But this is why I
Yeah.
asked you where you don't have a finite. This is why I asked you where you have a finite. Theorem about the finite.
Exactly. Yes, because this non-standard analysis allows you to lift.
Conceptual approaches.
Yes. So yeah, so I actually managed to prove it. That's nice.
Yes, that is a 2 minutes past. There also.
Yes.
If you have more questions, you can ask the copy.
Oh, yes. Oh no, I don't need a jacket.